Here. Perfect. All right. So like I said, today what we're doing is we're looking at angles, okay? And in order to do that, there was one word that I've mentioned a couple of times. I even took a problem off on our first homework about this because it wasn't something that was super important that we had to go into in that first unit. And it was this, is if I had something kind of like a point, right? I had a point, maybe let's just call it A. And then out in the distance somewhere, it didn't matter the direction, there's another point B, where A can go to B and keeps going on. Does anyone remember what that's called? It's a ray. Yeah, and it says so right there in the notes, so you can look there too. But yeah, a ray. And all a ray is it's a line, right? But it's only part of it. It's not going the other direction this time, right? It doesn't have anything on the other side of my endpoint. And that's what this says, is it's part of a line consisting of collinear points, right? Points that are on the same line, but only on one side of a chosen endpoint. For example, A to B. There's points all over here that I can look at, but there's nothing on the other side of A, right? That is a ray. And now the question is, well, what's the point? Like, what's the value of a ray for us, for what we need to do? And here's what we're getting to. An angle, like a formal definition of an angle. This is a definition we can work with. An angle, if you want to rely on it, it's right here. Okay. An angle is a pair of rays with a common endpoint. Okay? If I take another ray out to maybe some point C, that should look pretty familiar, should it not? It's an angle. An angle is a pair of rays that share a common endpoint, A. Okay? What questions do you have about what an angle is? Okay. Now let's talk about it. Let's actually work with this a bit. Whenever I have a ray, I label it just the same as I've labeled lines before. Except this time, there's a starting place, is there not? And since there's a starting place, that's where my first point is going to be. So if I were to label this, it kind of gives me a visual here to work off of. I can call this ray A to B. And what symbol do I have here on the top that tells me it's a ray? It's a ray. Yeah, it's literally the symbol. It's one arrow, not two. But notice I could also call it A to C. It's like I'm going in order like I've done before. But can I go backwards this time? Why can't I go backwards this time? There's direction. Exactly. There's no backwards this time. There's a direction you follow. First period had this interesting question. Let's say I had a point D, like that, right? Is this the same thing as DB? Is that the same thing? Maybe if it was a line going backwards and forwards, right? But how do I know that A is involved here, my endpoint? How do I know that that's my starting point? Do I? No. So when I'm talking about this, what I'm saying is I need to make sure that where I start is in the name I give my ray, right? What I'm saying is A has to be the point I start with. Any other point's fine. I just make sure I have two, but I need to have A where I start, okay? What questions do you guys have about how I name rays? That lets us name angles now, okay? We're sequencing it so that by naming the rays this particular way, we can now name angles. When you name an angle, you name the angle based off of 3 points, A, B, C, whatever 3 points you have. You name it with 3 points where the second one is your shared endpoint, your common endpoint. So what is a name I could give to this angle right here? I need 3 points where the second one is the shared. How do I name that? B, A, C. What else can I call it? C, A, B. Exactly, where the second one is the shared point. And when I specifically say it's an angle, you know what I draw next to it? A little angle. Okay? Angle BAC. Or angle CAB. That's how I name an angle. Okay? Some last remarks, and then we'll kind of move forward. Some vocab words that would be good for us to know, right? Some of the objective of what today is understand the vocab, so that way moving forward this week we have the language we share together about what we're talking about. If I have 2 rays that go in opposite directions, what do I call that? You can look there, right there. What are they called? They make a straight angle, but what are the rays themselves called? Opposite rays. So creative of mathematicians. They're literally like, they're just rays going in opposite directions. Opposite rays are just 2 rays that go in opposite directions, and they form a straight angle. With how many degrees? 180. Exactly. Like I said, today's objective is that we are just formalizing what we've done before into a common language we can share. And this angle that's made, this straight angle, makes 180 degrees. Cool. And then the last thing, when I make my angle with my pair of rays, right, the rays that make my angle, these are called sides. They're just the sides of my angle, okay? And the point that they share, make sure I can bring this down a little bit. There we go. Cool. If I ever am not trying to write something and you can't see it, please let me know so that way I can adjust it. The 2 parts of my rays are called my sides, right? These rays that are made up. And then the shared endpoint, that endpoint they have in common, that is called the vertex. Okay? It's called my vertex. It's kind of like my elbow, right? My elbow is my vertex of my arm, where I have my 2 rays going in different directions. So, what questions do you guys have about any of these terms that we've talked about, any of how we label rays or angles or any of this information that we've dug into so far? I want to make sure it's clear. How are we feeling about it so far? Out of 5, how are we feeling about it so far? Out of 4, 5. Okay. About a 4. Okay. Just trying to get a quick gauge. Thank you, guys. We'll see if we can get it up to a 5. So, go ahead and turn the page. Like I said, today's point is just kind of getting through some notes, just seeing what we can do. And then that way, moving forward, we'll just be able to move super fast. All right. Now, every single time we've ever done anything in this class, it's always been under the assumption that it's on a flat surface, right? Any work we've done on the boards, these boards are flat surfaces. Any piece of paper we've drawn on, those are flat surfaces. Points, lines are all on planes, right? when you put an angle on a plane, in other words, whenever you make an angle, okay, you divide whatever plane it's on into three distinct parts, okay? The first is this, the angle itself. That is one piece that makes up the entire plane. It's just the angle that you're on. And so that's what it says right here. Points D, A, B, and C lie on that angle. That's the first thing, right? The second thing, though, I kind of think of it like this. Have any of you guys ever played like the original Pac-Man? Like, super old game? Are we all familiar with who Pac-Man is at least, right? Yellow old guy who just eats all the dots and tries to get away from the ghosts? Well, think about this, is that if I have some sort of angle like this, well, then that's kind of like Pac-Man, almost, that he's going to go and eat some points, right? Because he's got those, like, sharp teeth right here. There we go, right? And he's going to go eat something. He can only eat the dots that are inside of the game, can he not? And so the second sort of space that we say is in our plane, whenever we draw an angle, is called the interior, or the inside, right? All of the points that Pac-Man can eat. All of this blue shaded region, right? So G, F, H, those are different points that Pac-Man could eat on the interior, on the inside. Okay? And then the last of the three distinct places, well, the stuff outside, right? The exterior. All of the points and things that are on the other side of this angle that we make. So maybe points I, J, and K. Any point that Pac-Man cannot eat. Okay? As an illustration, if this is not clear enough, if I have some sort of kind of 2D flat surface like this, with an angle that we've made before, right? A, B, and C. The first of my three distinct places is the angle ABC itself, right? So any points that are on this angle, that's my first place they could be. The second could be maybe like a point D, something in the interior of that angle that Pac-Man could actually eat. Or the third place, anything on the outside, in this like shaded spot that Pac-Man can't eat anything out there. Okay? That's the three places that we divide planes into. That becomes important when we dig into something called slope, and we're able to look at areas under some lines, right? Are they on the interior of that angle is a similar question to fill in the shaded region, right? And we'll be able to talk about that when we get there. So, what questions do you guys have about how in the world we divide the plane with an angle? Okay, cool. Example 1. Let's actually play around with these labels and words that we've been digging into. Right, example 1. It says we need to use this figure to identify the angles or any parts of the angles that satisfy these conditions. So, here's kind of the picture. I think, like I said, the point of us having the book was just so that way we can have the visuals in common right there in front of us. It says name all the angles that have D as a vertex. So let's think about it. D is a vertex. What is a vertex? Not exactly the center, but yeah, the shared endpoint, which in this case is the center. Yeah. And so, looking at what it's already given us, we know that EDF, right, if we're kind of illustrating what we have, E is up here to D to F. So there's one that has D as a vertex. It gives us EDG, there's one with the vertex right there. F to D to C. We've got G to D to C. It even says F to D to H. What's one that we haven't given yet? Yep, look at what's there, what we haven't used yet. Yeah, sorry, Charles, yeah. C to D to H. So what he's saying here is C to D to H, right? It has that shared endpoint. So C, D, H. What's another one? There's a lot we could go with. Yeah. B to D to C, absolutely. B, D, C. As long as it's the second point in our name, and that it's the shared endpoint between two sides of our angle. Part B, name the sides of angle 2. So find angle 2. Yeah, our sides. So we have A, B, D. Those are our 3 points. So if it's asking for the sides, what is it asking for? Yeah, so it's asking for the rays. What are the names of the rays that make that angle? So we have BA, right? Because B has to be where we start. B is our starting point on that angle. There's 2 again, just so it's clear, there's 2. So we have BA, and what's the other one we could put? BD. Yeah. We could also say BG, because G is on that same path too. We could go with that, but just keeping it simple, we could just do BD. I don't want to move too fast. What questions do you guys have about parts A and B? Okay. Part C, name a point on the interior of angle FDE. So find FDE. What's a point on the interior? Right, here's FDE. The interior is all the stuff Pac-Man can eat. So what's a point that Pac-Man can eat? A. Could we eat B? Why not? It's on his jaw, right? That's kind of why I use that analogy, is that's not the same thing as being on the interior if it's actually on the angle. It's either on the angle, on the interior, or on the exterior, one of those 3 places. And then the last one, name a point, or maybe multiple, that's on the exterior of FDE. There's several. What are some points we can go with? C. Okay, what other ones? H. What else could we go with? G. Yeah. Anything that's on the outside of Pac-Man that he can't see, that he can't eat. So what questions do you guys have about using this vocab and labeling things? Okay. Now is an interesting conversation. We've got all these words we can use now. We've developed the vocabulary, right? We said point, line, planes. Those are our undefined terms. Then we defined some stuff, and we spent some time with those definitions. We built some axioms, right? Some statements that we don't prove, but that we know that they work. And then from there, we built like the segment addition postulate. And we're going to eventually, like I said, this is the proofs topic. We're going to be able to build theorems and bigger statements that we can prove, okay? Which means using something we've seen before, but translating it, and I think, like I said, I was trying to preview this with your test review a little bit. Page 67 right here, okay? This is an important concept that I don't want us to lose out on, okay? And it's this. Just like we had before, when we had some sort of line segment A to B, like this, A to B, and we were able to play like Fruit Ninja and like cut it right in half, right? We found a spot right here. What did we call that spot right in the middle? The what? The midpoint. Yeah, it's that spot right in the middle, the midpoint. And I would just call that C. I could call it M, whatever point, just to say it's in the exact middle. The term we used was it bisects the line segment. That was that term that we used, bisects. Or in other words, it cuts it exactly in half, so those two halves are the same length. What was the symbol we used to talk about bisecting? It wasn't an equal sign. Got a little squiggle. Ooh, congruency. It looks like this. It's like a little squiggle, and then like an equal sign under that. And I pointed out when we were going through the notes that the difference was when we say something is equal, 1 equals 1, right? All that means is that the numbers themselves are the same thing. So, as an example, 1 equals 1, right? 5 equals 5. It's the same thing, and it's only with numbers that we use the equal sign. When we're talking about shapes, we're going to use the congruent symbol because we're not talking about the exact same thing. What we're talking about is the length associated with those things. For example, A to C and C to B, are those the exact same thing as each other? No, they're not. But do they have the same length? Yes. So when we're talking about shapes, we use congruent. When we're talking about numbers, we use equals. That distinction becomes important because when we look here, we notice something. This whole bisecting thing we talked about with the midpoint extends to angle measurement as well. Whenever we're measuring an angle, right, trying to figure out how many degrees that angle is, what we're looking at, right, might be something like this. We got our two sides of our angle. Here's our vertex A, there's B, and there's C. Let's just assume, for example, that we have some number of degrees right there. It doesn't matter what number it is, it's a number. And on the interior of my angle BAC, right, this is angle BAC, I'm going to have some other point W. It doesn't matter. Some point W on the interior. I'm going to play the game, connect the dots, and I'm literally just going to connect A to W with another one of my rays. But notice, I cut the angle in half. That means they are congruent to each other. The two parts of my angle that add up to the whole is the same kind of question as when we were working with line segments and saying the little parts of my line segments added to the whole. Except now I call these congruent angles. That's what this is talking about right here. Angles that have the same measurement are called congruent angles. And we write that, you see how I have that weird squiggle symbol right there? QTR and STR, however you want to label those, are congruent. They're not equal. The angles are congruent. I'll put a pause right there. What questions do you have about congruent angles? I don't want to go too fast. Okay. Here's the distinction now. This is what I was getting to. The numbers associated with those angles, those are equal. Okay? So it goes on to say right here, a ray or a segment that divides an angle into the two congruent parts, like we just saw with W, right? This ray AW here is an angle bisector. Bi meaning two, sector as in part, two equal parts. The angle is cut into two equal parts. So in this figure that we have right here, we have Q, T, and R. What is the measure of angle QTR? 60 degrees. And what is the measure of angle STR? 60 degrees. See how I'm talking about numbers here? I'm not talking about the shapes. I'm talking about the numbers associated with those shapes. Those are equal. The distinguishing thing to help us out here is whenever we have a tiny little letter M outside of the angle symbol. That M stands for measure. That's what M stands for here, is measure. The measure of angle QTR, which is different than just the angle itself, QTR. Okay? So if we have that little M, that means we're using the equal sign. So if you want to take that down, M implies equal sign. No M, right? If there's not an M right there, then we're going to use the congruent symbol. So, what questions do you guys have about angle bisectors, how we notate them and label them, or anything involved in using them? Okay. With that being said, this is what I want you to do. This is a problem similar to what we were just doing. You can work by yourself or with your group at your table. Try doing this check right here. It says in the figure, ray K to M and ray K to J, they're opposite rays. That just means they go in opposite directions. And then it says K to N bisects angle JKL. If the measure of JK to N is 8x minus 13 degrees, and the measure of angle NKL is 6x plus 11, find the measure of JKN. There's a lot going on right here. See what you can do for just about 30 seconds. We'll break this down. Okay. Let's break this down a little bit, okay? First and foremost, all this whole opposite rays thing is saying is that if I needed to, what would the measure of this angle right there be? 180, okay? It's a straight line, back and forth, okay? And then it says this, KN, ray KN, bisects JKL. So here's JKL, J to K to L. Bisect means what can I say about the two interior angles here? Let me ask that again. The two interior angles that have been divided, if it's bisecting, what can I say about their measures? They're the same. So I'm going to put little dashes just to say that those are the same. Okay? It says that the measure of J to K to N is 8x minus 13. And then n to k to l is 6x plus 11. How do I set this up to solve for x? Yeah.
6x plus 11 equals 8x minus 13.
Exactly. 6x plus 11 equals 8x minus 13. Why?
Because if you solve for x, and you input one of the equations, you get your angle.
Exactly. That's that process I'm going to do. We've seen this before. This was what we did with line segments. Now we're just doing it with angles. And so now we play the game and solve for x. I'm going to subtract 6x on both sides, and I'm just assuming here that we've done this process enough times to kind of follow the steps, right? 6x minus 6x, that cancels away. What is 8x minus 6x? 2x. So 2x minus 13 equals 11. I'm going to add 13 on both sides. So 24 equals 2x. So what is x? 12. I divide the 2. And now I plug it into where? Where do I want to plug that into? 8x minus 13. Why? That's jkn. So I'm going to take x and plug it into jkn. 8 times 12 is 96, I believe. Is that right? Minus 13. So, yeah, 96 minus 13. I have to, 8 minus 3 is 3. 83. 83 degrees. And that's what we're doing now, right? The point of today was for us to have some vocabulary in our belt so that when it comes to angles this week, as we play with it more and more, we can solve valuable problems for us, okay? So when we come back tomorrow, we're going to spend a little bit of time going through this last piece on like the special cases of things, right? And then we'll be able to play around with this throughout the week when it comes to angles. So that way, moving forward, we've got everything in our tool belt. We can start proving some stuff. Cool? So we've still got about, I believe, 1 minute to get your guys' things. I hope you have a great rest of your day, you guys.